key thing that Maxwell did was to consider charge continuity equation, charge current continuity equation. What does that mean? Charge is conserved. That is what it means. Charge is conserved. What do we mean by that? In the universe, the plus and the minus charges are the same. That hasn't changed ever. So this charge being conserved, when we say there is a current, we say that the current is flowing, right? The charge is flowing. Yeah. The charge is flowing means what charge that flows from one part, it goes to another. But if you were to see the totality of it, the charge is conserved. So if this guy is the amount of current that is flowing through, this is the total current I that is flowing through that surface, that is equal to how much is the charge that is decreasing. Yeah, it is it's equal to the rate of decrease in charge. That means the current has already flown out. If the current has flown out, that means the charge inside has decreased. How much is the current that is flowing out is equal to how much the charge has, the rate at which it decreases inside. How? Because current is the rate of flow of charges. So in that sense, how much this guy is the rate. Rate means change in time. Yeah, rate means change in time. The rate of decrease in charge. So this has to be, otherwise you're creating charge somewhere, isn't it? If there is current that is flowing, if that is equal to how much that has been decreased inside, that means charge is conserved. You're not creating any charge. Charge cannot be created or destroyed. Yeah, all the charge is conserved. You can only separate the plus and minus charges, but they are all conserved. So having said that, next few slides are going to be mathematics, but the consequence of it is important. So when you take this guy, this is what charge continuity means. Yeah, divergence is the source or sink of current. Yeah, divergence J means how much is the current net outgoing flux. Yeah, how much is the source of current? The source of current is going to be the decrease in the charge density, the rate of decrease in the charge density. If you go ahead and substitute in the Ampere's law, which is given as it is like this, when we take the divergence of this expression, when you take the divergence and apply to this guy, you notice that divergence of J becomes 0 because divergence of curl of any vector field is equal to 0. This is mathematically true. This is an identity, mathematically true. So what Maxwell saw was, hey, if I go ahead and do this, I notice that my divergence J is equal to 0. It is not equal to this. So charge continuity fails, yeah? So he was a mathematician after all. So he was thinking, hey, how come this be 0 while this is not being satisfied? Does that mean the charge continuity is violated? He went on to research it, and turns out, yeah, this is the person, Sir James Clerk Maxwell. Then he noticed that no, there is no inconsistency provided the curl H is equal to J was the original Ampere's law, but I can extend the Ampere law by adding this new term. When I add that new term, if I do the divergence of curl of H, I end up getting the charge continuity equation naturally. The divergence of J is equal to this. So the charge continuity is valid. So what Maxwell did was to introduce this guy by extending Ampere's law. So that's the beauty of mathematicians, right? Faraday was a physicist, Ampere was a physicist, all these guys, Gauss was a mathematician, yeah? But these guys, they observed some experiments, they formulated the theory, they tried to explain it with mathematics. Maxwell was purely a mathematician, and he came about to come and see that, hey, how come there is a violation of continuity equation? Then he just introduced this term, the highlighted term, and turns out that everything is consistent now. So his fundamental contribution, this term, the dou D over dou T, is going to be equal to what is called as the displacement current density. It's called as displacement current. So there's a term J and there's a term dou D over dou T. Both are currents.